All right, so for those of you who are listening through the recording, I'm going to do some examples of hypothesis tests today using StatKey. And the first thing I'm going to do is share the steps that we need to go through to do a hypothesis test. All right. So step number one would be stating the null and alternative hypotheses using symbols. And these are examples of how you would do that. For example, if the problem states that the null hypothesis is 100, so we would say, and it's a mean, we would say mu is equal to 100 next to h naught colon. This is exactly the way we'd write it. And then the alternative of hypothesis, if it's a what's called a left tail test, would be that mu is less than 100. So less than refers to a left tail test. And of course, we use HA for the competing or alternative hypothesis. Notice the numbers match 100, 100. All right, they always have to match. Right tail test, this is an example. Population proportion, for example, could be, for the null hypothesis, could be 0.27. And versus, I guess I spelled versus wrong there. No problem. You know what I mean. And the alternative hypothesis is that p is greater than 0.27. So greater than symbol means right tail test. And if you have a two tail test, this is an example where mu is equal to 50, the mean is equal to 50 versus mu is not equal to 50, right? So in most cases, it'll be very clear to you whether you have a left tail test or right tail test, because the researcher, whoever's making the claim, is stating that the value should be greater than or less than the null hypothesis. Now, the problem won't say null hypothesis, it's going to give a value, population value, and then the researcher will claim whether it's less than or greater than. If there's no claim less than or greater than, then most likely it's going to be not equal to as the test. So that's what you do, number one. And number two, you create a randomization sampling distribution in StatKey, which I'll show you how to do. Number three, once you have the randomization sampling distribution, you're going to take the original sample statistic, whether it's a sample mean or sample proportion, and you're going to go into that distribution in StatKey and replace one of the numbers that I'll show you where it is, one of the numbers, which is an endpoint for the distribution. You're going to replace it with the sample statistic. You're going to type it in. And then you're going to look at the following. For a left tail test, the proportion to the left of the sample statistic is going to be called the p-value. I'll define what a p-value is in a minute. For a right tail test, the proportion of to the right of the sample statistic is the p-value. And for a two tail test, what you're going to do is you're going to take the proportions in the left and the right tails, add them up, and that'll be the p-value. And then you're going to compare this p-value, which is a probability, to the alpha, which will be given in the problem. That's the level of significance. And if the p-value is less than or equal to alpha, we're going to reject the null hypothesis. If the p-value is greater than alpha, we're not going to reject the null hypothesis. So that's the rule, decision rule. And the interpretation, when it's written, always begins with at the blank percent significance level. In other words, you're going to take your alpha, convert it into a percentage, and that number is going to go into this blank, right? So if alpha is 0.01, it would be at the 1% significance level. Then you would state something like there's enough evidence to reject the null, or there's not enough evidence to reject the null, whatever the problem is talking about. All right, so that is it. Those are the 6 steps that you would go through. Pretty straightforward once you see how it's done. So what we're going to do now is take a look at a couple examples, and then I'll show you the ones that I picked out. I picked out 4, but I'm just going to show you how StatKey works with hypothesis tests first. Hold on a second. Let's see if StatKey is open. Yeah. All right. So let me open up StatKey for you. All right, and this last column here, randomization hypothesis test, is what you're going to use for a hypothesis test if you were going to create these yourself. So there are 4 that we will be looking at: test for a single mean, test for a single proportion, test for differences in means, test for differences in proportions. This last one we're not going to use. Let's look at for the test for a single mean, see what it looks like. So there are examples here. I think I might have even shown you this one last time, the body temperature one. I could try picking out another one here. Let's see. Yes, mammal gestation days. Try that. So there are 40 mammals. I don't know what mammals they are, but anyway, there are 40 in the sample, and the gestation days are measured for each one of these mammals. I guess they're different mammals because they're so different in gestation days. So 40 mammals, maybe out of a zoo or something, are chosen at random, and their gestation days are measured, and the mean ends up being 194.325. So this is a sample statistic, the sample mean. All right. And suppose the null hypothesis is that the mammals, on average, have a gestation days of 200 days. Right, 200 is the average. And suppose we want to do, suppose the problem states that we want to see if it's less than this. All right, so the null hypothesis would be that mu is equal to 200, that's the null, and we want to test to see if the alternative hypothesis, we want to test to see if it's less than 200. So mu is less than 200, it's going to be the alternative. All right, so we'll just state that. And then if it's less than, that means it's a left tail test, so we're going to end up clicking this left tail box here, right? So it's pretty easy to figure out. If the alternative, we always look at the alternative hypothesis. If it has less than, we're going to click the left tail. If it's greater than, we're going to click the right tail. And if it's not equal to, we're going to click the 2 tail. All right, very simple. All right, we're just going to generate 1,000 of these called randomization samples. All right, they're going to be randomly selected with a mean of 200. Not all. And what's going to happen is we're going to generate individual samples with different means. For example, if I choose one sample, this mean is 194.6. If we choose 40 mammals at random, if we choose another one, it's 217.125. So every sample is going to have a different mean. And if we generate 1,000 of these things, okay, the null mean is 200. Let's plot it right here. And we're going to do a left tail test, right? Because we're going to say the alternative hypothesis is, as a researcher, we're going to say that the mean is less than 200. So click the left tail. Now the left tail automatically defaults to 0.025. All right. Now, the way we're going to do the hypothesis test, we could, of course, change this to what alpha is. You know, if alpha is 0.05, we could change this to 0.05 if we want. And then look at our sample statistic and see if it's in the red area or if it's in the black area. In this case, it's 194.325. So that's obviously in the black area. So in the red area here, this is the reject region. And then the black area is the do not reject region. So it looks like 194.325 is in this do not reject region. And we're going to not reject the null hypothesis. But the way I want you to do it, instead of doing it this way, where we click for alpha here, what we're going to do is we're going to click down here. And this is the endpoint I was referring to in the instructions. And I'm going to click it and type in the actual sample statistic. So I'm going to click that in, and I'm going to type in 194.325. Now for a left tail test, according to the instructions I gave, The area to the left of the sample statistic is the p-value, and that's this here, 0.44. Now, what is a p-value? The p-value says it's the probability of getting the sample statistic or something more extreme than that, which means further away from that, from the actual null hypothesis. So we're going to assume the null hypothesis is true, and we want to plot. We're going to plot the sample statistic, and for a left tail test, the area to the left of the sample statistic is this thing called the p-value, right? And it's 0.44. Now, if we had originally picked, remember last time I had mentioned that researchers select their probability of a type 1 error, which is called the level of significance. They choose that ahead of time before they do the research. They pick a low number like 0.05. So if we picked alpha as 0.05, what we're saying basically is we're comfortable in rejecting the null hypothesis up to 0.05, because that tells us the probability of a type 1 error. We're okay with a 5% or less type 1 error, but we're not okay with something bigger than 0.05. That's what we mean when we choose alpha as 0.05. We're saying, if the type 1 error is greater than 0.05, we're not good with that. So it is in this case here. 0.44 is much larger than 0.05. So we're not going to reject the null hypothesis. In other words, this sample statistic is too close to the hypothesized value of 200 to reject it. All right? We're only going to reject the null hypothesis if this p-value is less than alpha, the level of significance. If it's not less than or equal to it, we're going to not reject the null hypothesis. So that's what we're going to say here. So if we had alpha as 0.05, which is 5%, we would conclude something like this. We would say at the 5% level of significance, there is not enough evidence to reject the null hypothesis. The mean number of gestation days is 200. There's not enough evidence to reject the null hypothesis. Mean gestation days is 200, right? And we could also say, in addition to that, and then conclude that it's less than 200. We don't have enough evidence to do that. All right, so this is the p-value method. This is the method that most researchers in the real world use. They will publish their p-value. Of course, they always want, if they want to reject the null hypothesis, they want their sample to provide enough evidence to reject the null hypothesis, so that their selection of the alpha, the level of significance, is important. Now, as I mentioned, I believe last time, every field of study has their own typical alpha that they use. So it's not like you can just fudge, right? You can't go, do your research and then say, all right, I got 0.44 here. I'm going to make my alpha 0.5 so I can reject the null hypothesis. No, you can't do that. It's cheating. All right, you have to select a low alpha ahead of time and then see how the research pans out. And in this case, it didn't pan out for the researcher. This particular sample indicates that there's not enough evidence to go with the alternative hypothesis that mu is less than 200. All right, so this is an example where we do not reject the null hypothesis. But just remember, when we do the interpretation, we always have to state what alpha is in a statement like at the 5% level of significance. We have to state that before we write anything else with our interpretation. All right, so this is an example of a left tail test for a single mean. All right, left tail test for a single mean. All right, suppose we wanted to do a right tail test for a proportion. I'm going to go back and let's do a test for a single proportion. Notice it automatically defaults here to 0.5 for our null hypothesis. It doesn't have to be 0.5. It could be any proportion between 0 and 1. Okay. Suppose I wanted to create my own proportion. They do have samples here where they have different proportions, but suppose I wanted to create my own. A proportion, remember, is the count divided by the sample size. For example, a political poll, you're counting the number of people who like candidate A out of so many people who are surveyed. So if we sampled 1,000 people and 540 of them like candidate A, it means our proportion is going to be 0.54, and you can see it right over here. All right, so the count divided by the sample size is the proportion. So this would be the sample proportion. So suppose that the null hypothesis is that P is 0.51, 51%. Suppose that's the null hypothesis. You can change the null hypothesis right there. And this is our sample proportion. So what we're going to do, we'll generate some samples. Let's generate a couple thousand of these samples. By the way, what we're generating here is called a randomization sampling distribution. Each one of these dots represents a random sample of 1,000. Excuse me, of 1,000. The sample size is 1,000 of people, let's say, who are selected, and we are asking them how many of you like candidate A. So in this particular sample, the one that we, or this one here, 531 out of 1,000 like candidate A. Pick another one, 513 out of 1,000 like candidate A. And there's 1,000, there's 2,000 of these samples that we chose. All right. Now, if we want to do a right tail test, then we're going to click the right tail button. In other words, the null hypothesis is going to be that P, the population proportion, is 0.51, and the researcher thinks it's bigger than that. So the alternative hypothesis will be P is greater than 0.51. So we'll see the red dots here on the right. Now it automatically defaults to 0.025 on the right tail. And once again, what we're going to do is we're going to take our original sample statistic, 0.54, and actually look, this is interesting. It actually is already here, isn't it? 0.54, that's just a coincidence. Just a coincidence that 0.54 happens to be the sample proportion. That typically doesn't happen. So if this wasn't 0.54 here, we would have to click it and then type in 0.54 as the sample proportion, right? And actually, when I did it, it actually changed this, which is kind of strange. But anyway, so I typed in these. So just get into the habit of doing it anyway. Just click the endpoint, this box down here. Replace whatever's in there with the sample proportion. This is the original sample proportion. And then what shows up here is the p-value. It's the number. It's the proportion of all of these dots here that are the red dots. This is the proportion that of sample statistics that are as least, that are the sample value that we got, or something more extreme, in this case greater. All these are greater than 0.54. And it ends up being, this is 0.026. Suppose our alpha is 0.05 in this case here. And we notice our p-value is less than that, 0.026. So 0.026 is less than alpha, the level of significance, 0.05. And in that case, we would reject the null hypothesis that p is 0.51, and we would say that the null hypothesis, that the alternative hypothesis that p is greater than 0.51 is probably true. The true population proportion is bigger than 0.51. And the reason for that, well, the sample statistic is sufficiently far away from 0.51 where the p-value, the area to the right in this case of the sample statistic, is less than our alpha. Remember what alpha is. It's the probability of a type 1 error, and it's basically the maximum percentage or maximum proportion of all samples. It's the maximum proportion that we're willing to accept, where we're going to accept the null hypothesis true, and yet we're going to reject the null hypothesis. All right. So the type 1 error is the maximum type 1 error that we will accept. Notice in this case that if alpha is 0.05, 0.026 is smaller, so we'll accept that for sure because it's less than alpha. We just won't accept an alpha, or excuse me, a p-value bigger than alpha. Now, notice also, and I have to make this really clear to you, that if your original alpha was 0.01 instead of 0.05, we would come to a different conclusion. If alpha was 0.01 originally, 0.026 is bigger than alpha, and therefore we would not reject the null hypothesis. That may sound kind of strange to you, right? In one case, we're going to reject it. In another case, we won't. But it all depends what we select as our alpha or level of significance at the beginning of the research process. And typically, people select something that is a standard within their field of study. And many fields into social sciences, for example, pick 0.05. I believe that the harder sciences like chemistry and physics and all, they like 0.01. So it depends on your alpha whether you reject or not reject. That's why in the interpretation you would have to stay at the beginning at the blank percent level of significance. If it's a 5%, we would say at the 5% level of significance, we would reject the null hypothesis that p is 0.51, and we would conclude that it's bigger than 0.51. If we selected it originally alpha is 0.01, we would say at the 1% significance level, there's not enough evidence to reject the null hypothesis that p is equal to 0.51. So this is the way most researchers do their research. It sounds strange, but that's what they do. They calculate up front, or they determine up front their alpha, their maximum type 1 error that they're willing to take on when they reject the null hypothesis. And then they determine through the sampling process and the research whether they have a p-value that's less than or greater than that alpha. If it's less than or equal to that alpha, they're going to reject the null hypothesis. If it's greater than alpha, they're not going to reject it. Any questions about that? Again, this is something that you sort of have to do a couple of examples with, just to get your feet wet with it. Let's do another example. Go back and let's actually do difference in means. Now, these two tests here, tests for difference in means and difference in proportions, are assuming we're comparing two groups of people or things instead of just looking at one group, one population. We're looking at two populations. Let's look at the difference of means. Okay, and let's find one that I think we would, yeah, commute time. Let's do this commute time one here. All right, now it says commute time Atlanta versus St. Louis. Atlanta is going to be population 1, and St. Louis is going to be population 2. Now, when we have more than one population, we're going to assume the two populations are independent of one another, right? And therefore, they could have different sample sizes. All right. Now, in this particular case, 500 commute times are shown in Atlanta, because the population 1 is Atlanta, and the population 2 is St. Louis. There's 500 commute times sampled in St. Louis. But these numbers, these sample numbers, these sample sizes don't have to match if we have independence here between the two. Now, the mean for the Atlanta commute time, I guess this is in minutes, all right, These are probably 500 commuters in Atlanta, 500 commuters in St. Louis, and it's just the amount of time to get from their house to the workplace. And suppose the average for these 500 Atlanta people is 21.97, 29.11, right? Yes, 29.11 minutes is the average for these 50 here. And then for the 50 St. Louis, it's hard to read, but it says 21.97, 21.97 minutes, the average commute time for St. Louis commuters. So X, now the sample size symbol is X bar for means. And we're subtracting, we're finding the difference between the average commute time in Atlanta and the average commute time in St. Louis. So we're going to subtract these two numbers, 29.11 minus 21.97, and we get 7.14. That's the difference in the two average commute times. All right. Now, how does randomization work with two samples? Well, you randomize within each sample. All right, within each population, you do randomization. All right, and we're going to end up with, for each sample, we're going to end up with an Atlanta sample and a St. Louis sample, each with 500, but with different sample means, with different mean commute times for each of these randomization samples. Now, suppose the null hypothesis is that there's no difference in the average commute times between Atlanta and St. Louis. Typically, that's the case when we're dealing with two different populations. The null hypothesis is basically the two are equal. Now, I hope you can see mathematically that if we subtracted U2 from both sides, U1, we would have U1 minus U2 on the left and 0 on the right. So if the two commute times in the null hypothesis are equal to each other, the two mean in the null hypothesis, then we can also say that U1 minus U2 is equal to 0. All right. Okay, I hope that makes sense. And now let's suppose that the alternative hypothesis will say that there is a difference between Atlanta and St. Louis. We're not saying Atlanta is bigger than St. Louis. We're going to just say there is a difference between the two. We're not sure whether it's Atlanta bigger or St. Louis is bigger, but we're going to think that the two cities have different traffic patterns and all. We're going to state that their average commute times are different, which means that the alternative hypothesis would be that mu1 is not equal to mu2, or we could state it as mu1 minus mu2 is not equal to 0. Since this is a two-tailed test, because when we say mu1 is not equal to mu2, or mu1 minus mu2 is not equal to 0, the not equal to means a two-tailed test. We're going to click this box in the middle here when we do our randomization test. So if we just generate one sample here, you could see that the randomization sample has different sample means for 500 Atlanta commuters and a different one for 500 St. Louis commuters, and then you subtract Atlanta minus St. Louis, the means, x1 bar minus x2 bar, and in this case you get 0.97. So whenever we do these samples, what's going to be plotted is the difference between the two means. All right, that's what's going to be plotted over here. So let's plot 3,000 of these things. All right, yeah, 3,000 randomization samples. What's plotted along this axis is the difference between Atlanta and St. Louis average commute times. So when it's positive, when we have positive values here, like this one here, we see that x1 bar minus x2 bar is 1.45. You see it on the right here. Actually, let's do that one there. X1 bar minus x2 bar is equal to 1.51. That means that Atlanta average exceeds St. Louis average by 1.51 minutes, okay, on average. And then down here, let's just pick one of these down here. Oops. Let's pick that one. Notice that x1 bar minus x2 bar is negative 2.37. What does that mean? That means the Atlanta commute time is on average 2.3 minutes lower than St. Louis. All right. If Atlanta minus St. Louis average commute times is negative, that means the St. Louis commute time on average is bigger. And you can see that here because it says 26.726 for St. Louis on average, 24.354 for Atlanta on average. So St. Louis's average is bigger. All right, so these are, of course, are the differences in the, and that's what they mean by x1 bar minus x2 bar for each one of these 3,000 samples. It's plotting the difference in the average commute times between its two cities. We want to do a two-tail test. We want to check that one out. Once again, it just automatically gives us these faults of 0.025 on the left, 0.025 on the right for the number of red dots. Number of black dots is 0.95. This proportion of all dots is 95% of them is in the middle. Now, if we go back to the original sample, we look at the original sample says that the difference in the commute times for the original sample is that Atlanta has 7.14 minutes more on average than St. Louis. Now, in the middle here, the null is 0, right? Why is it 0? Because if mu1 is equal to mu2, and we subtract mu2 from both sides, mu1 minus mu2 is equal to 0. So what they're plotting here is the difference between mu1 minus mu2. It's that difference. It's going to be 0. That's our null. There's no difference between the two. And if the sample difference is 7.14, well, that's bigger than 0. So we're going to go over here to the right, because there's one to the left here also. But we're going to replace the one on the right because it's the bigger one. All right, it's the positive one, and we want to use the positive one because this is positive. We replace this with 7.14. Enter. And notice that 7.14 is way out here, and there's no dots for it, so it's showing a p-value of 0. Now, let's do a better example here. Actually, this is okay. Let's just assume this is fine. Now, it's showing that this number here is 0. It's showing on the left this number is 0. All right. In reality, p-values can't be 0, exactly equal to 0. They have to be some number between 0 and 1. But it's pretty close to 0. It's way out here. It's so far away from all these black dots that it's practically 0. Now, with p-values, this is very important when we do two-tail tests. The p-value is going to be the sum of these two numbers, this number plus this number. You have to remember that. You have to write this down. I do have it in the instructions. But when you do a two-tail test and you plot the sample statistic in one of these boxes here, again, if it's positive, you're going to plot it here. If it's negative, in this case, you plot it over here. You're going to add up these two numbers. It's always the sum of these two numbers for a two-tail test, right? Both of these have to be added up. In this case, it's going to be 0. So, and then you're going to compare it to alpha, the sum of those two to alpha. If the sum of the two is less than alpha, less than or equal to alpha, we reject the null, and greater than alpha, we're not going to reject the null. Well, this is a clear case where the sample statistic is so far away from 0. All right, this difference between Atlanta and St. Louis is so much different that we're going to conclude, we're going to reject the null and say there is a difference between the Atlanta commute times and St. Louis commute times. All right. Let's look at another example. See if do another example with the difference in the two means. Let's do another one where it's not as clear like that. Let's look at sleep caffeine words. I don't know what sleep caffeine words means, but so let's pick another one. I don't like that one too much. Brain size. There we go. Brain size. All right. So you have two groups. First group is some control group, and the second group is another group, like some experimental group. But the control group is group number 1, and the other group is group number 2. This at the bottom here is always group 1. And the average for the control group is 7602.6, and the average for the this experimental group is 6459.2. Whatever these numbers represent, doesn't matter. But so the difference between these two numbers, we subtract these two numbers, is 1143.4, and that's our sample difference in the means between the control group and the experimental group. There's 25 people in each group. That's what these two numbers mean. And suppose we're assuming that there's no difference between these two groups, the control and this, and we want to see if the experimental group is significantly different. So let's again do a two-tailed test here, and again we're going to generate some samples, a couple thousand samples. We'll do a two-tailed test. And it looks like this is going to again be a case. Well, we'll see. Now, again, we're going to take our sample difference between the two groups. Now, the null hypothesis is in StatKey is always set up so that the two groups have an equal means. So that means their difference is going to be 0. So that's going to be our null difference in the two means. And then we're going to put our sample difference. We'll put it over here because it's a positive value. If it was negative here, we would put it over here. We're going to click this box and type in their sample difference in means, 1143.4. And this is another example where we get, it's way out here somewhere. So again, 0 plus 0 is 0, that we're going to reject the null hypothesis. The sum of these two numbers is going to be 0. So again, I'm looking for actually, I'm looking for an example where we don't have a big difference. Let's try this one here, leniency in smiles. The first group is the smiling group, and the other group is the neutral group. And again, whatever the write-up is, we just have to look at the results of the two groups, whatever's being measured. Group 1 is the smile group. Group 2 is this neutral group. The average, I don't know what this number represents, but whatever it does, we're subtracting this number and this number, the two means, and we're getting 0.79. There's 31 in each group, or excuse me, 34 in each group, in each sample group. All right, this is our sample statistic, 0.79. We're again, the null hypothesis is there's no difference between these two groups. That means we subtract these two, we get 0. And again, we'll generate a couple thousand samples. Once again, let's do a two-tailed test, and I hope, I think in this case, we're going to get a reasonable answer. So this will be a better example. Now, we have 0.79 as our sample statistic. It is a positive number. So we're going to replace it over here. Again, if this was a negative number, we would have put it over here. So we're going to take our 0.79 and replace this number here with 0.79. All right. Now, this is where you have to be careful for a two-tailed test. All right, it's a two-tailed test. You're going to see a number here and a number here, basically usually the same number. And what we have to do is, with a two-tailed test, is to get our p-value, we have to add these two numbers. So the p-value is not 0.024, it is 0.048. It's this number times 2. It's these two numbers added together. So if our alpha is 0.05 and the sum of these two is 0.048, 0.048 is less than 0.05, we would reject the null hypothesis. So at the 5% level of significance, since 0.048 is less than 0.05, we're going to reject H naught. So in our interpretation, we're going to say something like, at the 5% level of significance, there is enough evidence to reject the null hypothesis that the SMILE group and the neutral group are the same means, and we're going to say that there's enough evidence to say that their means are significantly different from each other. All right, that's what the two-tailed test would say. Any questions about that? So this is a better example. Just remember, for the two-tailed test, where the null hypothesis is that mu1 is not equal to mu2, or mu1 minus mu2 is not equal to 0, we need to add up these two numbers after we've replaced one of these boxes with the sample statistic. Just remember to put it in the right spot. 0.79 would go over here because it's positive. If this was a negative number, we would have replaced it over here. Okay. Now, we did a randomization test for means, a randomization test for difference in means. What we're going to do next is we'll do the same for proportions. So we'll do a single proportion first. All right. And suppose our null hypothesis, we'll just create a null hypothesis for our population proportion. Let's assume it's 0.75. All right, so that's going to be our null. And suppose we want to, our alternative hypothesis is that P is less than 0.75. All right, so let's create some data. Let's create a sample set that, actually the one we have here is fine. Let's use this one right here. Our sample proportion is 0.64. That's less than 0.75, so this might work. Sample size is 25 people, 16 said yes or no to something, whatever it might be. And that means, let's say yes to a question. And so the proportion of people out of the 25 who said yes is 64% of 0.64. All right. So we're going to generate some randomization samples. Let's generate maybe 800 of these, 800 samples. All right. And we're going to do a left tail test in this case here, because our alternative hypothesis is that P is less than 0.75. We'll click the left tail, the left tail test, and then we're going to replace this number down here with 0.64. Type in 0.64, enter. And therefore, the number up here is our p-value. It's the area, it's the probability to the left of 0.64. Right, of getting a sample proportion of 0.64 or less than that. Right? That's our left tail test. And if our alpha, for example, was 0.10, 10% level of significance, this is bigger than, this p-value of 0.158 is bigger than 0.10. Therefore, we would not reject the null hypothesis. So we would say something like, at the 10% level of significance, there is not enough evidence to reject the null hypothesis that the population proportion is 0.75. Okay? And that's because the sample statistic of 0.64 is not sufficiently far away from the null value of 0.75 to conclude that we could reject the null hypothesis. It has to be sufficiently far away. That means it has to be less than or equal to alpha, which is 0.10, and it's not. Its p-value is bigger than alpha. All right, so that's how we would do a test for a proportion. Let's do a difference in proportions. There's difference in proportions. And I guess this is fine. I think this is a questionnaire where men and women were asked about divorce. All right, maybe they were married, and I guess yes would be they think divorce is morally acceptable. No would be they don't think it's morally acceptable. So 1,029 men were asked this question, and 730 said it's morally acceptable. 1,029 of females in the sample were also asked the question. 689 of them said it's not morally acceptable. So when we divide 730 by 1029, we get 0.709. That's a proportion of males in the sample who said it's morally acceptable. Divorce is morally acceptable. And the sample proportion for females is 0.67. Okay. Now, with proportions, whatever is listed first here is going to be population 1, and the second one will be population 2. So male minus female. Actually, this is where we want to look. We want to subtract their proportions. We get 0.04 approximately. So let's say we wanted a right tail test, right? So the null hypothesis is that the two populations, the males and females, there's no difference. Basically, there's no difference in terms of whether one thinks that divorce is morally acceptable or not, right? There's no difference between spouses in terms of that. And the null, let's make the alternative hypothesis that more men than women say that divorce is morally acceptable, more men than women, which means that P1 is bigger than P2. Right? Remember, the first one listed here is group 1. This is group 2. So P1 greater than P2, or if we subtracted P2 from both sides, it would be P1 minus P2 is greater than 0. All right? So 0 is going to be in the middle. And any negative numbers would mean what? It would mean that females say it's more morally acceptable than males. And if it's a positive number, it would be more males than females. Okay, so let's generate a couple thousand samples. Okay, null is here. And again, the null hypothesis that we're saying is that we believe, the alternative hypothesis, we believe males are more willing to say it's morally acceptable, divorce is morally acceptable than females. So that means P1 minus P2 is greater than 0. All right, so we're going to do a right tail test. Does that make sense? It's right tail, right? Because P1 minus P2 is greater than 0. Greater than 0. So the greater than symbol means right tail. And once again, it all automatically defaults to 0.025, but we take our proportion or sample proportion of 0.04. It looks like it's already here, but we're going to type it in anyway. You do that anyway, just to double check. And you see here that the p-value is 0.023. All right. So for any one tail test, like a right tail test or a left tail test, whatever you come up with, once you've entered your sample statistic into here, whatever comes up here is your p-value. So the p-value is 0.023. If the level of significance, alpha, is 0.01, we would say, we would conclude that we would not reject the null hypothesis because 0.023 is bigger than 0.01. However, if our level of significance is 0.05, then it's a different conclusion. 0.023 is less than 0.05, therefore we would reject the null hypothesis. So that's why in our interpretation, we always start off with our level of significance, right? We would say at the 5% level of significance or at the 1% level of significance, and then make our conclusion based off of that. All right, so you notice in everything we've done here so far, no formulas, right? There's no formulas involved. And typically in a regular statistics course, you would be doing some formulas, you're using calculators, software, whatever you might be using. Here, we're just using stack key and doing simulations and coming up with a answer based off the, and what do we do? We're just plotting along the x-axis here. We're plotting our sample statistic. All right, we're plotting it and then determining the probability that is for all those values that are at least the sample statistic or more extreme than that. Okay, any questions about that? So I think we've done all 4 cases, haven't we? We've done in a single mean, a single proportion, difference in means, difference in proportions. Okay. So let me just show you what I've come up with. There we go, I think it is. See if I can find these screens here. Yeah, photos. All right, so here is a screenshot of a randomization of X. So what these what it says up here is randomization dot plot of X bar. That means these are 1,000. These are 1,000 samples. Okay, and the mean is the null hypothesis is 30. U is equal to 30. Now, if you look at what's checked off up here, can you tell me what kind of test is this? Is this a left tail test, a right tail test, or a two-tail test?
Two-tail.
Two tails, right? Based on what you see here, suppose I've already entered into one of these 2 boxes here, right? I've entered the sample mean, all right? Remember, we have a sample, and this obviously is not the difference in means, right? It's just one sample mean that was plotted here. It's either one of these 2 numbers here. We don't know which one by looking at this by the way. But suppose we did enter the sample mean. What is the p-value?
.0070.
Okay, anybody else? Remember, this is a two-tail test.
0.014.
That's right. For a two-tail test, notice we have red dots on both sides. We need to add these two numbers here, because all the black dots in the middle are not part of the p-value. So, I mean, one way you could figure out the p-value if you want to is just take 1 minus the number in the middle here. But this number plus this number, 0.014, you have to remember to do that for a two-tail test, all right? That's why I'm showing this to you first. You need to remember to do that one. All right. Let me see. Go out of this one here. Stop sharing. Let's see if I can pick out the other ones. Let's see if this works. There we go.
Excuse me, Professor, but we'll be going over more examples of how to find the proportion.
What do you think? I'm doing it now.
Thank you.
Yeah. Exactly what I'm doing. All right. So let's see. I don't know if this is the proportion one. That's a two-tail. Hold on. Let me check this one out here. Or for me to see these things. All right. All right, here's a proportion one. First of all, state what the null hypothesis is.
0.5.
Correct. What is the alternative hypothesis? Now, when you say 0.5, no, that's not good enough. Tell me the null hypothesis, the whole thing.
P equals 0.5.
That's right. You have to say the whole thing. 0.5 is meaningless. It doesn't mean anything. A lot of students, by the way, when they write these down, if they were actually writing down, they always forget, they just write down 0.5 as if that means something. It doesn't mean anything. You have to state the population parameter. You have to state equal to or whatever symbol you use in between, and you have to then say the number 2. So P is equal to 0.5 is correct. Now, what is the alternative hypothesis? And remember to use the symbols and everything for me. What is the alternative hypothesis?
P is less than 0.5.
Exactly right, because it's a left tail test. Left tail means less than, all right? Tell me what the p-value is. Assume that I've entered into the box at the bottom here, the samples proportion, 0.461. Suppose that's the sample proportion. What is the p-value? There's not many more choices on here.
Is it just 0.015 or is it P
No.
equals 0.105?
All right. P-value. I'm saying it's not a hypothesis. The p-value is a probability. So what is the answer?
Just 0.015.
Right. Okay. So correct. That's the p-value. When I say p-value, it's P-VALUE. All right. Now, if alpha, the level of significance, is equal to 0.0, if it's a 1% level of significance, do we reject or not reject the null hypothesis, and tell me why?
What was the level?
1%.
We would reject it because this one's larger.
What's larger?
The p-value.
And you're saying we would reject?
Yes. Yeah.
All right. So here's the rule. If the p-value is less than or equal to the alpha, we reject. If it's greater than alpha, we don't reject. So what do we do in this case?
We don't reject it.
Right, because the p-value is larger than the alpha. What if my alpha is 0.05? Do we reject or not reject? And tell me why.
The
level of significance. Go ahead.
Yeah, then we would reject because it would be less.
What is less? Just to state it in words, so complete words.
If the p-value is less, then we
right.
Yeah, then we reject.
Right. In this case, it is right. 0.015 is less than 0.05. Right. That's what you would say, basically. We would reject the null hypothesis. All right. So if we reject the null hypothesis, then do we feel that there's enough evidence to go with the alternative hypothesis? Is that true? Yes or no?
Yes.
Yes, of course. Because they're competing hypotheses. If we have enough evidence to reject the null hypothesis, that means we feel that there's enough evidence to support the alternative hypothesis. Okay? Just like in a jury trial, if you feel there's the prosecution has given you enough evidence beyond a reasonable doubt, you will convict the person on the charge. In other words, you'll reverse the presumption of innocence, and you'll say, I think they're guilty, even though I didn't see the crime, right? The jury person didn't see the crime, but they believe there's enough evidence to conclude the person committed the crime. The same thing here. The p-value is basically giving you the probability. If the null hypothesis is true, it's the probability of getting the sample statistic or something more extreme than that. So think about it. If we reject the null hypothesis, right, but the null hypothesis is true, the probability of that happening or something more extreme is 1.5%. That's pretty small, right? That's a small probability of that happening. That is, to get a sample with a sample proportion of 0.461 when the population has a proportion of 0.5. Is this sufficiently far away from the 0.5 where we would conclude that the null hypothesis value is for the population is probably less than this, not 0.5. That's really what we're trying to say. Okay, and when we reject the null hypothesis, what we're saying is that it is sufficiently far away. We can make that determination. We're comfortable in rejecting the null hypothesis. Now, as I said, if alpha is 0.05, we're going to reject in this case, right? Because 0.015 is less than 0.05. The reason why we're rejecting is that we're saying, I'm willing, as a researcher, to reject the null hypothesis when the null hypothesis is actually true. In other words, I'm willing to make that mistake if that mistake is 5% of the time or less. See what I'm saying? That's what the alpha 5% means. All right, it's basically saying I'm willing to accept up to a 5% error when I reject the null hypothesis. Well, with the sample that I have here, the error is 1.5% error as opposed to 5%. If you're willing to accept up to a 5% error, aren't you willing to accept a 1.5% error? See what I'm saying? The answer is yes, right? If you're willing to accept up to a 5% error, type 1 error, you certainly are willing to accept a 1.5% error. That's why the rule says if the p-value is less than or equal to alpha. Anything less than alpha, or even equal to alpha, you're okay with that. You're willing to reject the null hypothesis, and you're willing to have that as your error, type 1 error. But if your p-value ends up being bigger than alpha, well, you said 5% is the biggest type 1 error you would possibly want, okay? And if you got something like 0.25 as your p-value, well, that's too big. That's the probability of the actual probability of a type 1 error. Well, that's too big. So you're not willing to reject the null hypothesis in that case. That's sort of the logic behind it. That's why it works the way it does, right? And, you know, in the beginning days, this may not be clear to you, but I think if you think about it for a while, hopefully it will come to you that this is a logical way of doing it. All right, so so these are examples here that I just showed you, a couple of examples. Stop sharing, and let me just do one more thing here. Let's go back, share screen, and let's see if there's another one here. There's one. I don't know if I showed you this one. Let me see. Did we do this one? I think we did this one, didn't we? All right. So anyway, I think I showed you enough cases like this, the 4 different types of hypothesis tests. I tried to show you a left tail test, 2-tail test, right tail test. I will post these examples with solutions probably by Friday or so. All right, I'll have everything written up and posted so you can look at it. So basically, that's it for hypothesis tests, because typically in a real course, a real statistics course, we would be going over more formulas. There'd be different, types of formulas, and but these randomization tests, it's actually a lot simpler for you guys. So what I showed you is basically it in terms of the types of questions I can ask you. The things that I just asked you in terms of questions, that's it. I can ask you, what's the null hypothesis? What's the alternative hypothesis? I can ask you, what's your what's your sample statistic? I might have to give you that information. I might have to ask you something about, I can ask you what the p-value is. I can ask you what's your decision, and you would make that decision. I can give you an interpretation question saying, is this the right way of writing it? Okay, that sort of thing. So anyway, on Monday will be a quiz. The quiz will go over all this stuff that we went over today. And it's just the basics of it. Nothing, there's not going to be any heavy duty problems, just some basic things. And then we have our test next Wednesday, a week from today. And that test will cover probability and confidence intervals and hypothesis tests. So I'll do a review of that on Monday, just give you an idea of what to be looking for when you review for your test. All right, and then the following Monday, I believe that's the 14th, is when your final exam is. And that'll be it. All right.
Wait, so did you say we had a quiz Monday?
Yes.
No.
One
Okay.
more quiz. I promised 9 quizzes. That's quiz number 9. Yeah.
Okay, thank you.
So you're going to have 9 quizzes, and I'm going to average all those 9 quizzes. So there's plenty, hopefully you did well in most of them, and that'll give you a decent average for that. And then, the 3 tests, and then the final exam. So, but I'll go over all of that next week also with you. All right, any questions? I think that's it. I think it's 3:15. So I'll stop the recording. No other questions?